this video, we're going to talk about Cauchy Euler equations. So Cauchy Euler equations. So here's an example of a Cauchy Euler equation. X squared y double prime plus 3x y prime plus 2y equals 0. So the reason this is a Cauchy Euler differential equation is because the power of x matches the order of the derivative. See, here the power of x is 2, here the order of the derivative is 2. Here the power of x is 1, here the order of the derivative is 1. Here you can think of there as being an x to the 0, and you can think of y as being the 0th derivative. So that's what it means to be a Cauchy Euler differential equation. Here's another example. X cubed y triple prime minus x squared y double prime equals 0. This is also a Cauchy Euler differential equation. Here the power of x is 3 and the order of the derivative is 3. Here the power of x is 2 and the order of the derivative is 2. So in this video, I'm going to give you the steps to solve a Cauchy Euler differential equation, and we'll do a simple example. So these steps are for the following differential equations. So steps to solve. Let's say we have an order 2 differential equation, ax squared times the second derivative plus bx dy dx, that's the first derivative, plus cy equals 0. Okay, so step 1. So some people memorize the characteristic equation or the auxiliary equation. I like to do it from scratch every time. So step 1 would be to let y be equal to x to the m. So we're assuming that our solution has this form. Then what you do is you take derivatives, so you differentiate it as many times as needed, okay? And then you plug into your dE. So plug into the dE, and then you solve for m. So solve for m. So in this case here, in this specific example, what you would do is you would take the derivative twice and plug it in, right? And then you would solve for m. If you do that, you would end up getting am m minus 1 plus bm plus c equals 0. So this is a quadratic equation. And then you would solve it. So some people memorize this equation. Again, I like to do it from scratch. So when we do an example, you'll see we'll start with this. We'll take the derivatives and we'll just plug it in and go. All right, step 2. So when you solve the quadratic equation, you have 3 possibilities. So the first possibility is that you get distinct real roots. So if you get distinct real roots, say m1 and m2, and the solution is given by c1 x to the m1 plus c2 x to the m2. Okay, this should remind you of solving equations like, y double prime plus y equals 0. When you did these, you had sometimes you would get distinct real roots, except you would have e. You would have e to the m1, and then you would have e to the m2. Same thing, except here it's not e, it's x. So that's the first case. So distinct real roots, you get distinct powers of x. The second case is if you get a repeated real root. Repeated real root. Say m. So in other words, we have some repetition, right? We have repetition. So in this case, you would get y equals c1 x to the m plus c2. And whenever you get repetition, so before when we were solving homogeneous equations, we would put an x. It's very similar, except this time we put an ln x. So it'd be x to the m times ln x. I put it in the back, but you can also put it over here in the front. So whenever you have repetition, you multiply by ln x. Sometimes, if the multiplicity of the root is higher, you have to keep multiplying by ln x. For example, if it was multiplicity 3, you would have plus c3 and then x to the m ln x squared. 3. The last case is if you have complex conjugates. So complex conjugates. So in this case, the formula would be y equals, let me give you the conjugates, alpha plus or minus beta I. So in this case, the formula would be x to the alpha, x to the alpha, and then c1 cosine beta ln x plus c2 sine and then beta ln x. And that's what you would get if you had complex conjugates. Okay, let's go ahead and do maybe just one simple example. Okay, so let's see, here we go. EX means example. So solve, how about x, y double prime, plus y prime equals 0. So this is a Cauchy Euler Differential Equation in disguise, right? Because if you multiply the whole thing by x, you get x squared, y double prime, plus x, y prime, okay? And that would be equal to 0, okay? So in this case, it is Cauchy Euler because the power of x matches the order of the derivative. The power of x matches the order of the derivative. Okay, so our first step is to start by letting y be equal to x to a power. So solution. So we'll start by letting y be equal to x to the m. This is really easy to differentiate. You just use the power rule. So for the first derivative, you just bring the m down, and then you subtract 1 from the exponent. So m minus 1. That's a really weird looking x. Okay. Then we have to do it again because we have the second derivative. So y double prime. This time we bring down the m minus 1, and then the m, and then we get x to the m minus 2. Beautiful stuff. All right, now all we have to do is plug everything into our DE and solve for m. So we have x, and then plugging in y double prime, that's m minus 1, m, x to the m minus 2, plus y prime, that's m, x to the m minus 1, equals 0. Did that kind of fast. So this is our y prime that went in there, that's here. And then this is our y double prime. We can combine these. Usually after you plug this in, there's some simplification. So you want to group together the x's next, okay? So 1 plus m minus 2 is m minus 1. So this will be m minus 1, m. You can add the exponents. So it'll be m minus 1, right? Adding these exponents gives you m minus 1 plus m, x to the m minus 1. And this is equal to 0. Now what you can do is factor out your x to the m minus 1. So x to the m minus 1, this is m minus 1, m plus m equals 0. Now you just divide by this. This just goes away because you could divide by it. So you would get m squared, distributing, minus m, and then plus m. Oh, wow. Pretty cool. The m's cancel. So you get m squared equals 0. So m is equal to 0, and this has multiplicity 2 because it's repeated twice. So multiplicity 2, because it's really m minus 0, right? So it's really m minus 0 squared, right? So it's a repeated real root of multiplicity 2, and that root is 0. Okay, so that means our answer is going to be y equals c1 x to the 0, right, plus c2, and then it's repeated, so we have to have ln x times x to the 0. Okay, so at y equals c1 plus, and then we just have c2 ln x. And that would be the solution to the differential equation. So I hope this video made sense. It was kind of long. In the videos that follow, you'll find more examples. That's it. In this problem, we're going to solve the following differential equation. X squared, y double prime, minus 2y equals 0. This differential equation is known as a Cauchy Euler Differential Equation. The reason is all of the powers of x match the order of the derivative. So here, the power is 2, and then here the order of the derivative is 2. Here you can think of it as x to the 0, and you can think of y as being the 0th derivative. So this is a Cauchy Euler Differential Equation. Some people memorize formulas to do these. I do, but I do it a little bit differently. I like to start by letting y be equal to x to a power. And we know our solutions should have this form. So then you take the derivative. So then y prime, you just put the m in the front, you use the power rule, then you subtract 1, so x to the m minus 1. Then you take the derivative again, so y double prime, so you put the m minus 1 in the front, so m minus 1, m, x to the m minus 2. So you start with this always, take the derivatives, and then just plug them in. So we have x squared, then y double prime, that'll be m minus 1 times m, x to the m minus 2, minus 2, x to the m, and that's equal to 0. Okay, we should be able to combine some like terms. X squared times x to the m minus 2, we can add the exponents. So this will be m minus 1 times m times x to the m, minus 2, x to the m, and that's equal to 0. All right, so now we can factor out x to the m. So x to the m, then we have m minus 1 times m, minus 2, and that's equal to 0. If x is not 0, you can just divide by x. So we end up with m squared, distributing the m, minus m minus 2 equals 0. So this should factor. Let's try it. So m. We need two numbers that multiply to negative 2 and add to negative 1. I think negative 2 and 1 should do the job. Yep. So we get two possible answers. We get m equals 2 and m equals negative 1. But we said that y was x to the m. So whenever you have distinct real roots, the solution to the Cauchy Euler Differential Equation looks like this. C1 x to the m1 plus C2 x to the m2. So we can think of this as m1 and we can think of this as m2. So in this case, we have distinct real roots. So the final answer would be C1 times x squared plus C2 times x to the negative 1. And that would be the solution to the differential equation. So quick recap, whenever you have a Cauchy Euler, start by letting y be x to the m, take the derivatives, plug them in, simplify, you'll get some type of equation. In this case, we have distinct real roots. So the formula for distinct real roots is this one. And then all we do is we plug in the numbers, and that's it. It's pretty easy. In this problem, we're going to solve the differential equation. This differential equation is called a Cauchy Euler Differential Equation. The reason is the powers of x match the order of the derivative. The power of x matches the order of the derivative. And here you can think of it as being x to the 0 times y. So the power of x matches the order of the derivative. Recall that y is actually the 0th derivative. So we start all of these by letting y be equal to x to the m. The next step is to differentiate y and then plug it into the differential equation. So using the power rule, we bring the m down, and then we subtract 1 from the exponent, so we get m minus 1. Then we do it again, y double prime. This will be m minus 1 times m, and subtracting 1 we get x to the m minus 2. Now we're ready to plug everything into the differential equation. So we have x squared, and then y double prime is this piece here. So m minus 1, m, x to the m minus 2. Then we have 11x, so plus 11x, y prime, so that's this piece here. So m, x to the m minus 1. And lastly, we have 25y, so plus 25, and y was just x to the m. And this is all equal to 0. So again, step 1, you start by calling it y, take the derivatives, plug it all in. Once you get to this step, it's always the same, okay? You always want to group together your x's, so watch this. X squared times x to the m minus 2. When you multiply these, you'll add the exponents. So m minus 2 plus 2 is just x to the m. So we have m minus 1 m x to the m. Here, same thing. It's x to the 1 times x to the m minus 1. So that's just going to give us x to the m when we add them. So it's plus 11 m x to the m. And at the end we have plus 25 and then x to the m. That's all equal to 0. Now we can factor out an x to the m. That leaves us with m minus 1 times m plus 11m plus 25. And that's all equal to 0, right? So we have m minus 1 times m plus 11m plus 25. In the next step, we can divide by x to the m. So when we do that, it goes away. So we have m times m, so m squared. M times negative 1 is negative m plus 11m plus 25. All of this is equal to 0. Let's combine like terms. M squared, negative m plus 11m is 10m plus 25, and that's equal to 0. This actually factors nicely. This is m plus 5, m plus 5. It's actually m plus 5 quantity squared equals 0. It's a perfect square trinomial. So we get m equals negative 5, and the multiplicity is 2. So we have a repeated real root. So whenever you have a Cauchy Euler Differential Equation and you have a repeated real root, the answer is c1 x to the m plus c2 x to the m ln x. So in this case, m is negative 5, and we just plug everything in and we're good. So y is equal to c1 x to the negative 5 plus c2 x to the negative 5 ln x. And that is the final answer. I hope that makes sense. In this video, we're going to solve the following differential equation. So this differential equation is called a Cauchy Euler Differential Equation. And the reason is the power of x matches the order of the derivative. The power of x matches the order of the derivative. And you can think of this as being x to the 0 times y. So the power of x matches the order of the derivative. You can think of y as being the 0th derivative. Okay, so when you're doing Cauchy Euler equations, you always want to start, or one way to start, is to let y be equal to x to the m. Then you differentiate this and plug it into your dE. So this is pretty easy to do using the power rule. So you take the m, put it in the front, then you subtract 1, so you get m minus 1. Then you do it one more time, so y double prime. You take the m minus 1 and put it in the front. Then you subtract again from the exponent. So subtracting 1 one more time will give you m minus 2. So you call it y, let y be equal to x to the m, take the derivatives, then just plug everything in. So this will be 49 x squared. Then y double prime is this piece over here. So m minus 1 m x to the m minus 2 plus 49 x, and then we have y prime. So that'll be m x to the m minus 1 plus, then we have y. So that'll be x to the m. So when you get to this step, you always want to combine the x's. So you'll notice here we have x squared, and then here we have x to the m minus 2. So we multiply these, we're going to get x to the m. The same thing is going to happen here. X to the 1 times this is going to give us x to the m. Why? Because we add the exponents, right? So 2 plus m minus 2 is m. Likewise, 1 plus m minus 1 is m. Okay, so we have 49 m minus 1, m, and then combining these gives us x to the m plus 49 m. And combining the x's gives us x to the m plus x to the m. All of this is equal to 0. So now what you do is you pull out on x to the m. So x to the m, this will be 49 m minus 1. I wrote it a little bit differently. I don't know why I did that, but I just put the m in the front, plus 49m plus 1, and that's equal to 0. So at this point, you can simply divide by x to the m. So we divide both sides by x to the m, x to the m. So these cancel. So let's go ahead and distribute this. So 49m times m is 49m squared. Then here 49m times negative 1 is negative 49m. Then we have plus 49m, and then plus 1, and all of this is equal to 0. These cancel, boom. So we end up with 49m squared plus 1, and that's equal to 0. I guess we could solve this for m. We could subtract 1. So we would get 49m squared equals negative 1. And then to finish solving this, we would divide by 49. So m squared is equal to negative 1 over 49. Now we would just take the square root. And when you do that, you do get a plus or minus. And we also get an I because of the negative inside the square root. So plus or minus I. And then the square root of 1 is 1. The square root of 49 is 7. So we have something like 0 plus or minus 1 over 7i. That fits the form alpha plus or minus beta I. So we see that alpha is equal to 0 and beta is equal to 1/7. So we have complex conjugate roots. And whenever that happens, if you recall, the formula is y equals x to the alpha, bracket c1 cosine beta ln x plus c2 sine beta ln x. So alpha is 0, so we get x to the 0, so that's 1. So this will be y equals c1 cosine. And then beta is 1/7, so it's 1/7 ln x plus c2 sine, and then beta is 1/7, so 1/7 ln x. And that would be the final answer. In this video, we're going to solve the differential equation solution. This is a Cauchy Euler differential equation because the power of x matches the order of the derivative. Likewise here, you can think of there as being an x to the 0 power, and it matches y, which is the 0th derivative of y. Okay, when we're doing a Cauchy Euler differential equation, we always start by letting y be equal to x to the m. Now in this case, we have a third derivative, so we have to differentiate this thing 3 times. So we use the power rule. So y prime is m x to the m minus 1. All we do is bring the m in the front and then subtract 1. Then y double prime, well, you bring down the m minus 1. Then we have m, x, and then we subtract 1. So m minus 1 is m minus 2. Then we do it again. So y triple prime will be m minus 2, m minus 1, m x to the m minus 3. Okay, hard to read, but m minus 2, m minus 1, m, and then x to the m minus 3. So now we're going to plug everything into the differential equation. So we have x cubed, and then y triple prime. So that'll be m minus 2, m minus 1, m, x to the m minus 3, minus 6, and then y is x to the m. Whenever you're doing a Cauchy Euler differential equation, when you get to this step, you want to combine the x's. So we have x cubed and x to the m minus 3. When you multiply those, you add the exponents. So m minus 3 plus 3 is m. So we have m minus 2, m minus 1, m, x to the m, minus 6, x to the m equals 0. At this point, we can factor out an x to the m. So we get x to the m. Then here we get, looks like, I'm going to write it like this, m minus 1, m minus 2. Just arranging the order, m minus 1, m minus 2. Minus 6, bracket equals 0. We can divide by x to the m. that goes away. Boom, boom. So we have m. I'm going to go ahead and multiply this out. M times m is m squared. The middle term is negative m. The outer term is negative 2m. That means it's going to give us negative 3m. And then negative 1 times negative 2 is positive 2. Minus 6, and it's all equal to 0. So I just used some fast multiplication there. So m minus 1, m minus 2. So m times m is m squared. And then the inside is negative m. The outside is negative 2m. When you add those, you get negative 3m. Now we can distribute the m. So we get m cubed minus 3m squared plus 2m minus 6, and this is equal to 0. So now we have to try to solve this equation. So we have 4 terms, so maybe factor by grouping is a good bet. So we can pull out an m squared here. That would give us m minus 3. And looks like we can pull out a 2 here. That would also give us m minus 3 equals 0. So now we can pull out an m minus 3, and we're left with m squared plus 2, m minus 3, right? Pulling out the common factor of m minus 3 and writing it here equals 0. So we have a product equal to 0. That means each factor is equal to 0. So m squared plus 2 is equal to 0. And m minus 3 is equal to 0. This one's easy to solve. We just get 3. This one, we subtract 2, we get negative 2. When we take the square root, we get m equals plus or minus I square root 2. So it looks like we're going to have complex conjugates and a real root as well. So we can think of this as 0 plus or minus I square root 2. And then matches the form alpha plus or minus beta I. So you see that alpha is 0 and beta is the square root of 2. All right, so now we can use our formula. So this one is just going to give us c1x cubed. So that'll give us c1x cubed. And then these complex conjugates, they're going to give us plus x to the 0. So I won't write it, but x to the 0. Right? That's x to the alpha, so that's just 1. And then we'll have c2 cosine, and it's beta ln x. So beta is square root of 2, and then ln x, plus c3 sine, and then it's beta ln x, square root of 2, ln x. And that is the final answer. Remember, the formula for complex conjugates was x to the alpha c1 cosine beta ln x plus c2 sine beta ln x. So all you have to do is plug in the numbers, and that's how I got that. In this problem, we're going to solve this differential equation. So this is a Cauchy Euler Differential Equation. The reason is, if you were to multiply everything by x cubed, you would get x cubed times x is x to the 4th. And then here you would get plus 10x cubed y triple prime. And then you would notice that the power of x matches the order of the derivative. The power of x matches the order of the derivative. So it is in fact a Cauchy Euler differential equation. So whenever we're doing one of these, we always start by letting y be equal to x to the m. So we have a 4th derivative here, so we have to take the derivative 4 times. So using the power rule, we bring down the m, and then we subtract 1, so we get x to the m minus 1. We do it again, and then so we get m minus 1 times m, and then subtracting 1 again is x to the m minus 2. We do it again, and then we get m minus 2, m minus 1, m, x to the m minus 3, just keep subtracting 1. And then one more time, our 4th derivative would be m minus 3, m minus 2, m minus 1, m, and x to the m minus 4. Okay, now we're in good shape. Now what we're going to do is plug everything back into the differential equation and solve for m. Okay, that's what we're going to try to do. So we have x times that huge 4th derivative. So that was, let's see, m minus 3, m minus 2, m minus 1, m, and then x to the m minus 4, plus 10, and then we have the third derivative, which is here, right? Because it's 10, and then the third derivative. So m minus 2, m minus 1, m, x to the m minus 3. And that's all equal to 0. Okay, whenever you get to this step, you want to group together the x's. So like here you have x to the 1, and here you have x to the m minus 4. So when you add those, you're going to get x to the m minus 3. Then we're left with m minus 3, m minus 2, m minus 1, and then m. And then here we have x to the m minus 3. I'm going to put it in the front. So plus x to the m minus 3. Then we have 10, m minus 2, m minus 1, and then m. And that's all equal to 0. All right, so now we can factor out x to the m minus 3. So we have x to the m minus 3. And then we have m minus 3, m minus 2, m minus 1, m plus, and then 10, m minus 2, m minus 1, m bracket, and that's equal to 0. We can divide by the m minus 3, so I'm just going to go ahead and cross it out. And then here we have to figure out what to do. So let's see. We have m, m minus 1, m minus 2, m, m minus 1, m minus 2. Let's pull that out. So we have m, m minus 1, m minus 2. So if we factor that out, if we factor those guys out, we have m minus 3, boom, plus 10. Yeah, that works, right? M minus 3 plus 10. So we're just pulling this out and pulling this out, and that leaves us with m minus 3 and 10. Beautiful stuff, and that's equal to 0. So we have m, m minus 1, m minus 2, and this one looks like it's going to be m plus 7. That's all equal to 0. So we get 4 distinct roots that are all real. So 0, 1, 2, and negative 7. So the final answer to this problem would be y equals c1 times x to the 0, but x to the 0 was 1, so I won't write it, plus c2 times x to the 1, which is just x, plus c3 times x squared, kind of cool, plus c4 x to the negative 7. So that would be the final answer, and I hope that made sense. In this problem, we're going to solve the following differential equation. Solution. This is a Cauchy Euler differential equation because the power of x matches the order of the derivative, the power of x matches the order of the derivative, and here you can think of it as x to the 0 y. So the power of x matches the order of the derivative. You can think of y as being the 0th derivative. So to solve these, you always start by letting y be equal to x to the m. And then you take the derivative and you plug it into the dE. So here we use the power rule. So you bring down the m, then you subtract 1, so you get x to the m minus 1. Then we do it again. So now you bring down the m minus 1. You still have m, then you subtract 1, so you get x to the m minus 2. Now we plug everything into our differential equation. So we have 3x squared, and then we have y double prime, which was m minus 1, m x to the m minus 2, plus 6x, that's this piece here, and then we have y prime, which is right here. So m x to the m minus 1, plus y, which we said was x to the m. That's all equal to 0. So when you get to this step, it's always the same. What you can do is you can combine these powers of x, okay? So you have x squared times x to the m minus 2. You can add the exponents. 2 plus m minus 2 is m. So we get 3 m minus 1 m, and then x to the m, plus, here we have 6m, and then x to the 1 times x to the m minus 1. When you add the exponents, again, you'll get x to the m. Then here we have plus x to the m. It's all equal to 0. So now we can pull out x to the m. So we have 3m minus 1 m plus 6m plus 1 bracket equals 0. Then we would divide by x to the m to get rid of it. So these cancel. So let's see what happens. We can go ahead and distribute at the same time. Might make it a little bit easier. So, well, actually, I'll rewrite it. So 3, I'm going to put the m first. So 3m, m minus 1, plus 6m, plus 1 equals 0. Now we have to solve this equation for m. So I think a good step here would be to distribute this 3m. So 3m times m is 3m squared. Then 3m times negative 1 is negative 3m. Then we have plus 6m and plus 1, and that's all equal to 0. So we have 3m squared. Let's see. Negative 3m plus 6m is 3m. Then we have plus 1, and this is all equal to 0. Good stuff. All right, so how do we solve this? Well, we can complete the square, or we can use the quadratic formula. Let's go ahead and use the quadratic formula. So a is 3, b is 3, c is 1. The quadratic formula, if you recall, says that m is negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so this m here is going to be, let's see, b is negative 3, b is 3 rather, so we get negative 3, plus or minus, and then b is 3, so when we square it, we get 9 minus 4, and then a is 3, and then c is 1, all over 2a. So 2 times 3. Looks okay. So m is equal to negative 3 plus or minus the square root 9, and then 4 times 3 is 12, so we just get negative 3 all over 6. So if we break this up, we get negative 3 over 6 plus or minus the square root of negative 3 over 6. So that's negative 1 over 2 plus or minus I square root of 3 over 6. So we have complex conjugate roots of the form alpha plus or minus beta I. So in this case, alpha is negative 1/2, and beta is the square root of 3 over 6. Okay, so let's go ahead and write the answer out. So the form for this is y equals x to the alpha, bracket c1 cosine beta ln x plus c2 sine beta ln x. Okay, so this will be y equals, so it'd be x to the negative 1/2, bracket c1 cosine, and then beta is the square root of 3 over 6. So we have that. And then c2 sine, and again, beta is the square root of 3 over 6. And we have the ln x. Pretty scary looking answer. All right, so just using the formula and carefully plugging in alpha and beta. I hope that helped. Solve x squared times y double prime minus 3x times y prime minus 9y equals 0. This is an example of a Cauchy Euler differential equation. We know that because here the power of x is 2, and it matches the order of the derivative. Here the power of x is 1, and it matches the order of the derivative. And then here you can think of the power of x as being 0, and y is actually the 0th derivative of itself. Okay, solution. So we start solving Cauchy Euler differential equations by letting y be equal to x to a power. Then we differentiate this, plug it into our differential equation, and solve for m. So y prime, So we'll use the power rule. We'll put the m in the front. So we get mx to the m minus 1. We just subtract 1. Then we have a second derivative in this problem, so we have to do it again. So y double prime, and you put the m minus 1 in the front. So m minus 1, m, then you subtract 1, so you get x to the m minus 2. Good stuff. So now all we have to do is plug everything into the dE. So let's go ahead and do that. So we have x squared, and then y double prime. That's this stuff here, so I'm going to write it again over here. So m minus 1, m, x to the m minus 2, minus 3, x, and then y prime, that's this one. So m, x to the m minus 1, and then minus 9y, and y is just x to the m, and this is equal to 0. So every time you're solving Cauchy Euler differential equations and you get to this step, what you do next is you group the x's together. So here we have x squared, here we have x to the m minus 2. When you multiply these, you add the exponents. So 2 plus m minus 2 is just m. So we have m minus 1 times m times x to the m. Same thing here, it's 1 plus m minus 1. That's x to the m. So minus 3m x to the m, and then minus 9 x to the m. And this is all equal to 0. Then what you do is you factor out the x to the m, so x to the m. And this becomes m minus 1, m, minus 3m, minus 9. And that's equal to 0. Now you can divide both sides by x to the m. So if you divide by x to the m, these cancel, and then 0 over x to the m is 0. So we get m minus 1 times m, then minus 3m minus 9, and that's equal to 0. We can distribute the m, so we get m squared minus m minus 3m minus 9, and that's equal to 0. Good stuff. Let's see, we can combine like terms now. So m squared minus 4m minus 9, and that's equal to 0. So now we have a quadratic equation that we have to solve. I guess we could use the quadratic formula. Let's complete the square. That might be easier. So to complete the square, first maybe we can add the 9 to the right-hand side. So we have m squared minus 4m equals 9. Then what you do is you take the coefficient of m, divide it by 2, and square it, right? So negative 4 over 2 is negative 2. Negative 2 squared is 4. So you add 4 to both sides. So again, negative 4 over 2 is negative 2. And when you square that, you get 4. So we'll add 4 to both sides. So we get m squared minus 4m plus 4 equals 13. And this is called a perfect square trinomial, and it always factors. You just take this number and divide it by 2, and then you can keep the sign always, every single time, right? And this is equal to 13. To get rid of the 2, we take the square root. So we get m minus 2 equals, and when you take the square root of a variable squared, you always get a plus or minus. To finish, you just add 2. So you get 2 plus or minus square root of 13. So we have distinct real roots, okay? So whenever we have distinct real roots and a Cauchy Euler differential equation, the formula is C1 x to the m1 plus C2 x to the m2. So y is equal to C1, and then m1 is, I guess, 2 plus square root of 13. You could use the minus 1 as well. I'll just use the plus first, plus C2, whoops, I forgot the x. That's not good. And then x to the 2 minus square root of 13, right? So that would be your final answer, right? So let me write it again up here. It'd be C1 x to the 2 plus square root of 13 plus C2 x to the 2 minus square root. Solve the differential equation. Solution. This differential equation is a Cauchy Euler differential equation because all of the powers of x match the orders of the derivative. For example, this is a power of 2, and this order of the derivative is the second derivative, so it's 2. This is 1, and this is the first derivative. And then here, you could think of it as x to the 0. So the power is 2, and the order of y, the order of the derivative, is 0. Y is the 0th derivative, so it matches the power of x. Okay, whenever you have a Cauchy Euler, you can always start by letting y be equal to x to the m. Then just differentiate it and plug it into your dE. So using the power rule, y prime, you bring the m, put it in the front, so you would get x to the m minus 1. Then you do it again, so you bring that down, so you get m minus 1, m, and then you subtract 1, so m minus 1 is m minus 2. So you call this y, take the derivative, and use the power rule. Then plug everything into your dE. So we have x squared, and then y double prime is m minus 1 times m, x to the m minus 2, plus x, and then y prime was m, x to the m minus 1, plus 36, and then y is just x to the m. And this is equal to 0. So quick recap, you start with this, take the derivative using the power rule, plug everything in, and you end up where we are. At this point, you want to group together all the x's. So basically, we have x squared and x to the m minus 2. So when we multiply these, we add the exponents. So m minus 2 plus 2 is m. So we have x to the m, I'll put it in the front, m minus 1 times m. Same thing here, 1 plus m minus 1, that gives us x to the m times m. And then here we have x to the m times 36. Now we can factor out x to the m. So we have x to the m, bracket, and then we have m minus 1 times m plus 36. And this is equal to 0. Now you could divide by x to the m. So divide by x to the m. These go away. Okay. So then we get, let's see, so m times m is m squared. M times negative 1 is negative m. We have a plus m, right? That's this one. And then we have the plus 36. And all of this is equal to 0. Good stuff. These cancel. We get m squared plus 36 equals 0. To solve this for m, we can subtract 36. So we have m squared equals negative 36. And when you take the square root here, you will get a plus or minus. So taking the square root, we get m equals plus or minus 6i. So we have complex conjugate roots. We can think of this as 0 plus or minus 6i. That way it matches the form alpha plus or minus beta I. So when you're doing Cauchy Euler equations and you have complex conjugates, recall the formula was y equals x to the alpha, I'll use a bracket, c1 cosine beta ln x plus c2 sine beta ln x. Now all we have to do is plug everything in. Notice here alpha is 0, so that's nice, and beta is 6. So x to the 0 is going to be 1, so we don't have to write it because it's equal to 1. So we just have y equals c1 cosine, and then we said beta was 6, so this will be 6 ln x plus c2 sine, and again beta is 6, so 6 ln x. And so that would be the solution to the differential equation. I hope that made sense.